Before break, we did a chi-square test. It is a non-parametric test. There are two situations for chi-square test. One is a chi-square test for one sample. The other is chi-square test for a contingency table. Okay. Any questions? Okay, next, we are going to move on a new topic, logistics regression. Logistics regression, it is an extension of multiple regression, where the dependent variable, usually it is either 0 or 1, and independent variable could have a continuous variable, could be a categorical data. Okay. The model for logistic regression is expressed by EY equal to EXP. This EXP is the natural number. It's like E raised to power, for example, 5. Okay, so this E, it is actually natural number, etc., etc. Okay. And Y, it is either 1 or 0. The probability, so we have two events, either event A or event B, or not event A. The probability of event A occur, we use pi. Independent variable x1 to xk could be quantitative or could be qualitative. Usually, we use the logistic regression to predict the membership. For example, based on some parameters, I may predict, are you an international student or not international student? Are you living on campus or not living on campus, based on x1, x2, xk? Okay, so that is the idea of logistic regression. Okay, because we say EY equal to pi here, so that equation we write down to pi equal to this one. Pi represents the probability of event A occur. Rearrange this a little bit. So if we move this bottom, to the right, we get pi times 1 plus exp, beta 0, beta 1, x1, etc. Beta k, xk, equal to something on the top, exp, beta 0, beta 1, until beta k, xk. So we just rearrange that. This is pi times 1 plus this. So I take this bracket away, it becomes pi plus pi times exp. Do you agree? And then I collect like term, because I have exp here, collect like term, or I move this item to the right, then collect like term. I got on left-hand side pi, right-hand side I have pi times exp, beta 0, beta 1, x1, beta k, xk, plus exp, beta 0 plus beta k, xk. Okay, keep on going. Pi equal to, those two are like terms. Collect like term, you get, when I move this pi to the right-hand side, it becomes negative pi here. So negative pi plus 1 times exp beta 0 plus beta k xk. Okay, and then I move negative pi plus 1 to the right hand side. I get pi over negative pi plus 1 equal to exp beta 0 plus beta k xk. Okay, and negative pi plus 1 is the same as 1 minus pi. Okay, and then remember in mathematics, if you have, for example, a equal to exp b, if you have this, you take log on both sides, so you get log a equal to log and the exponential function cancelled out. You got log a equal to b. That is mathematical property. Okay. So here, both sides, I take log function, then log. Okay, and then left-hand side, I have log pi over 1 minus pi. Right-hand side, log and exp cancelled out. So I just have beta 0 plus beta k xk. Okay, and if I use pi star represent beta 0 plus beta k, and I get the equation here. So log. So this is how I get this point. Okay, and then so it is actually looks like the linear regression here. Linear regression. Okay, so this is how I derived the logistic equation to linear regression. And then we have an terminology odds. The odds of the event is the probability of the event minus the opposite, actually the complement of the event, the probability of y equal to 0. So pi over 1 minus over pi, that is the odds of the event. Okay, so for example, if pi represent today, we are going to have 20% chance of rain. I will ask you what is the odds. So the odds equal to pi minus 1 minus pi. If I have 20% chance of rain, I have 80% chance of not rain. So the result is 1 over 4. That is my odds. Okay. So another example, if I have 70% chance of raining today, what is the odds? The odds would be pi over 1 minus pi, 70% over 30%, so equal to 7 over 3. That is the odds. Okay. Any questions? Where is my online student? Oh, it's here. Okay. Any questions? Oh, just. All right. So the assumptions for logistic test is sample size. Make sure you have large sample size. Okay. And because the logistics test regression is the extension of multiple regression, remember one problem with the multiple regression, you probably have multi-collinearity, means maybe your x1, x2, x3 are related to each other. You don't want that to happen. So no multi-collinearity, okay? no outliers. Okay, if you have outliers, you may delete that outlier or replace the outlier with the average number. Okay. So large sample size, no multicollinearity, eliminate outliers. Let's look at an example. In this example, we have two variables. One variable is y. This example about ask people, do you have a digital organizer? 0 said, if you have no digital organizer, the value is 0. If you have a digital organizer, the value is 1, so that is y. Okay. And then we want to relate y to x. X is person income. Okay. So what we are going to do here, we want to create a logistic model between y and x, and then use this model to predict if I give you a person's income, can you make a prediction? Does this person own a digital organizer or not? Okay. So specifically, what we are going to do with this data, answer 3 questions. 1, define pi for this problem, and then define odds for this problem. Finally, fit data, use data to fit logistic model. Logistic model has another name. It is just logit model. Okay, so let's define pi for this problem. So pi represents the probability of owning a digital organizer. Okay, so pi equal to the probability of own digital organizer. Okay, that is the probability. So how do I know the probability? You count. How many total sample here? So total we have 20 people. And how many of them own the digital? You count how many one? Okay, there are 7 people. Okay, so the probability if 7 people own, okay, actually then 20 minus 7, 13 people do not own. That is the pi. Okay, 7 people own, 13 people do not own. Oh, that is the odds, sorry. Let's redo it. So the probability, pi is the probability of own digital. So I have 7 people. That is the probability. So the odds is the probability of own minus 1 minus. So the result is 7 over 13. That is the odds. Last question, use data to fit the model. Remember, when you have 1x, logistic model is this one. This is the logistic model. Okay. So first, you enter the data into SPSS. This data I also posted on Sakai. Go to resources on Sakai. You can get this data in either Excel format or in SPSS format. Sakai resources. I pause for a moment. If you want to follow my step along, you get the data first. So now I am going to open the data file in Excel or SPSS. Go to open. This one here, Logistic Digital. So I'm going to delete this one. So this is the data. Any questions to get the data? Right. This is the chart. Okay, so let's fit the model. Go to Analyze, Regression, and then Binary Logistic. Dependent variable is on. In logistic regression in SPSS, they call covariant. It is actually our X, or independent variable. And quick save button. We want to save probability. We want to save membership. And click continue. Under the options, we want to create classification plots. And then click continue. And then click OK button. So this is our logistic result. From this result, you can see we have 7. Actually, overall, let me double check my data. Looks like okay. Yeah, that's correct. So 13 people do not own. We have 7 people own. Okay, own the digital organizer. And this is classification table. Okay. The variables in equation. We have a constant. The coefficient is negative 0.619. This is just an exponential form for the coefficient beta b. So if you take EXP, go to Excel, just to show you. So if I can open Excel, any Excel, So in Excel, if you type in EXP negative 0.619, you will get 0.538. Okay, so that is the EXP, exponential function. Okay. And then we have variables not in the equation. They are not significant. So the income is actually not significant because the p-value 0.08 is greater than 0.05. And over here you have omnibus test of coefficient. Again, the p-value is greater than 0.05, so the model is not significant. So we cannot, this is not a good model. Based on the data, if you use Logistic, it is not good. I'll give you a next example later, okay? This example just to show you the procedure. Explain some statistics from the output. And in model summary, okay, you have Cox-Snell R square. You also have Nagicook R square. So those R square represent 13.6% to 18.8%. The changes in Y are due to the income. Okay, so the percentage changes is not good. Just for 13% to 18% are due to X. We hope that percentage is bigger. So that's another point to see this model is not a fit. And here we have classification table. Okay. We predict, see, this is the predicted. We predict 12 people do not own. We predict so this is similar to the classification table we did for discriminant analysis. And then if you want to write down equation, you can write down the equation based on these two parameters. But I do not want to write down equation because this model is not significant. Okay, so I don't bother to create equation to make forecast. So the purpose of this example is to show you, one, the procedure for logistic regression. Two, not all models are significant. This is an example. The logistic model is not significant. Although it's not significant, but the procedure, you see, they produce the probability. So for example, the probability for the first case is 0.244. Based on this probability, the computer predicts case 1 belongs to 0, not on. Now let's look at case 18. In case 18, the probability of on is 0.77. That's why the computer predicts this case 18 is on. Okay. Sometimes the computer predict correct. For example, case 18 predict correct, but in case 4, the actual number case 4, this person own a digital organizer, but the prediction said no, prediction is 0. Why predict 0? Because based on the probability 0.3, so that conclude this person not own. The cutoff point is 0.5. Anything about 0.5, the prediction is 1. The probability smaller than 0.5, the prediction is 0. similar to what we did in discriminant analysis. Okay. So this is this one. Any questions? Any questions? Oops. Let me check. All right, so now let's go to another example, discriminant analysis. And this example, by the way, the classification plot is so cutoff is 0.5. If our model is perfect, we would see many zeros on this side. We would see many ones on this side. But we see some 1 on left-hand side, we see some 0 on right-hand side, because the model sometimes do not make correct prediction. Okay. So this is example 1. And example 2. This is the data in example 2. We have one dependent variable y. The output for y is either 0 or 1. So 0 means not hired. 1 means hired. This is a human resource process, hire people, okay? Based on their education X1, years of experience X2, and gender. Okay. 0 represent male, or 1 represent male, 0 represent female. Sorry, this is not inclusive, okay? We should have OVGT, that category. Experience is number of years. So the first person have 2-year experience. This person have 10-year experience. Education is the years of education. So this person have 6 years total education. This person total have 8 years education, etc. Okay, so this is the data. So for this data, we need to answer 3 questions. Question 1, fit the data into logistic model. You got to write down a model. Question 2, is there sufficient evidence to indicate that gender is an important predictor of hiring status? Question 3, find EY when X1, X2, X3 is given. Okay, 3 questions. So now let's go to question 1 first. Fit the data into logistic regression. Again, this data I posted on Sakai under resources folder. In Excel format or in SPSS format. So now I will directly open it. So open. So logistic hiring. This is my data. So let's check the variable. I think I already defined variable. So the variable y, 0 not hired, 1 is hired. Okay. Education is years of education, experience, number of years working experience. So gender, 0 is a female, 1 is a male. So go back to this data. So go to analyze regression, binary logistic. Dependent variable is higher. Independent variable is education. Select all of them into covariates. Now, quick categorical. We have gender is categorical. Make sure first is selected. And then click continue. Under the save, we want to see the probability. And maybe this time I just want to see the group membership, not the probability, okay? The group membership is based on probability. I just need to see the result. Okay? And you could select probability. Okay? And then click continue. Then under the option, I want to create classification chart. Okay. That's it. Continue. Okay. So this is my output. Total, I have 28 people. 28 people. 15 are female, 13 are male. Okay. This is the classification table. Is this model significant or not? Usually you go to the model summary. Look at model summary. This model explains 51%, 51.8% to 72%. So 52% to 72% changes in Y are due to those 3 X. So pretty good. As you can see, this example, the percentage is significantly increased compared to our first example. Okay, our first example is 13% to 18%, and this example 52% to 72%. And over here, we have these variables in the equation. Okay, we have education X1, experience X2, gender X3. Looks like the education is not significant because the p-value is 0.055. Okay. And experience is significant because p-value 0.03. Gender is significant, 0.031. Okay. Because we have one variable, education is not significant, I want to delete education variable, rerun logistic regression. Okay. But before I delete, I want to copy this. This is my initial analysis. Copy maybe this up to here. Okay. Into OneNote. From here, the model overall is significant. Explain 52% to 72%. Okay, the R square. And Also, the ominous bus said the model is significant. But over the coefficient here, this is not significant. So next time I want to delete education, just leave experience and gender to rerun this logistic regression. Okay. So go back to the data. So analyze, regression, logistics. Is this the one? No, this is not the data file. I need to open another one. This is the first example. Okay, this is the one. Okay. No, this is not the one. Try to open my Excel file. Yeah, this is the one. Okay. So this time, analyze, regression, binary logistics. I want to delete education variable so that I just have experience and gender. Okay. Everything else remains the same. So just double check, save. Okay, that's right. Options, okay. Then you click OK button. And this is the model without education. Without education. Without education. So looks like those two variables still significant, experience and gender. Okay. And the model explain 40 to 56% because we lose one variable. Okay. So you can maybe make predictions based on this result. So I'll just copy here because the question also asks you to write down an equation. Okay, so this is our beta 1, beta 2. Constant is my beta 0. Oh no, is this one? This is the first. I should copy this one. So copy screen and paste. Okay, so I decide just use two variables, experience, gender, and constant. Okay, so constant is my beta 0. Beta 1 experience, beta 2 is gender, beta 0 is constant. Based on these three numbers, I can write down equation. So the equation is EY equal to EXP beta 0 plus beta 1 X1, beta 1 corresponding to experience, plus 3.83 times gender over 1 plus EXP. Copy down this number again. This is my equation, regression equation, logistic regression equation. Okay, so I answered the first question because this question asks us to fit the model, fit the logistic model. I have that model. And question 2, is there sufficient evidence to indicate gender is important predictor of hiring process? The answer is yes, because the p-value for gender is significant. p-value is significant, smaller than alpha. Okay. And question 3, find EY when x1 equal to 4, x2 equal to 0, x3 equal to 1. Remember what is our x1 represent? Our x1 represent education. We actually delete that variable. So we just need to plug in x2, x3 variable. Okay, so x2 is 0, x3 is 1. X2 represents working experience, x3 represents gender. So predict EY, so EY equal to EXP, negative 5.59 times 0.645 when experience equal to what? Equal to 0, x2 equal to 0, experience. Times 0 plus 3.83, gender is 1. 1 plus EXP, negative 5.59 plus 0.645 times 0. 3.83 times 1. Okay, so what would this number give us? So EXP, negative 5.59, this is 0, plus 3.83, 1 plus EXP, negative 5.59, plus 3.83, equal to EXP, negative, this is a 6, $1.76, negative 1.76. Is that correct? No. 9 minus 3 is 6. 9 times 5. Yeah, correct. So how do I do this? Excel. Where's my Excel? So I want to calculate that, okay? So equal EXP, negative 1.76 over 1 plus EXP, negative 1.76, so 0.146. So I just want to copy this. So this is answer for question C, prediction. The probability of this person who is female or who is male and who has no working experience is 0.14. So would you like to classify this person as hired or non-hired based on this probability? Anyone? Non-hired, you don't hire this person. Probability is small. The cutoff is 0.5. If the probability is 0.5, you hire this person. If the probability is smaller than 0.5, you do not hire this person. Okay? So that concludes our lecture on logistics regression. It is just the extension of regression, except we use exponential function here. Okay, the model, the theoretical model, this is 1x. If you have many x, the logistic model would become this one here. Any questions? All right. So I'm going to stop recording. Shall we take a second break?